Alright, so now that we've looked at growth, we're going to look at the other side of this with exponential equations, which is called decay. We're going to see how that works, and we'll keep using that idea of the zombies to help us do this. So it says, read through the following situation and answer the questions that follow to learn about exponential equations. So Zombie Apocalypse Part 2. After the outbreak occurred, scientists worked hard at creating a vaccination. Unfortunately, the vaccine only cures half of the individuals it is given to on a particular day. So if there are 240,000 zombies currently in Illinois, how many zombies will be left after the vaccine is administered? So this time what we're going to be multiplying by is a half. So you can do it as 0.5 or 1/2. So I'm going to take 240,000 times a half. So that gets me down to 120,000. The next day, they administer it again, and only half of the people get cured. So we're down to 60,000. Do it again. $30,000. $15,000. Then 7,500. $3,750. $1,875. $937.5. $468.75. And $234.375. Alright, so just like last time, we'll graph our data and then we'll take a look at the graph that forms. So the x-axis will be the number of days. There's 10 of them. And the y-axis will be the number of zombies. Okay. For this one, we probably should go by 20,000s. This is 20,000, 40,000, 60,000, 80,000, 100,000, 120, 140, 160, 180, 200, 220, and 240 would be way at the top. So I know it's not on our graph, we can keep extending it so we get the idea. Alright, so first off we can answer how many zombies are cured on day 10. We're going to round that to a whole number, which is 234. Can we find the cure, or the number of people that were cured on day 11? Let's take a look. So 240,000, I'm going to graph it, is up here. 0, 240,000. And it's 1 and 120,000. That's right there. 2 and 60,000. 3 and 30,000. 4 and 15,000. 5, and then down here I'm just going to keep going a little bit lower each time, getting closer and closer. So now we see the same type of graph, but this time it's decreasing instead of increasing. It's that same like hockey stick shape, but it's the other way. How could you find the number of zombies cured for day 11? Well, we could just keep going with our table and do another half. So times 1/2 is 117.1875. Again, we're not going to round, so we're going to leave it at 117 zombies. Which equation correctly models the zombies cured each day if you started with 240,000 zombies? So looking at the first equation, this is an x, just as a normal variable. This would be a linear equation. Our graph is not a line, so it can't be A. For B, this is a cubic, and remember cubics take the shape of that weird swivel. Our graph is not swiveling, so I'm guessing it's got to be C. And taking a look at it, we can compare. If we hit y equals, and you plug in the values for our problem, notice it's 0.5 instead of a half, it's the same number, and hit second table, you should be able to see the same numbers that we had going down the graph. And also if you graph it, we're not going to see anything because the numbers are too big, but if you hit zoom fit, which is number 0, you'll see that same type of graph that we were looking at in terms of shape. So this is called exponential decay. When a graph falls, it's called decay. So this is called an exponential decay equation. The general form is the same that we've been working with. It's y equals an initial value times b to the x. How is this equation different from an exponential growth? Remember, our previous equation was this. Our new equation is this. So the difference seems to be what's inside the parentheses. The number in front is different, but it's not a different value in terms of being a decimal or not. This one is a number that's less than 1. So the b value is less than 1 and bigger than 0. Alright, so where does decay come into play? This normally comes into things that depreciate or lose value. So it could be cars, it could be equipment, it could be population decline. Let's look at some examples. So Sterling bought a car for $20,000. The car's value depreciates 5% each year, and then given this equation, fill in the table and determine what, that should say Sterling, what Sterling car will be worth after 4 years. So go to your calculator, y equals 20,000 is the initial value of the car, 0.95, and then to the x. Oops, make sure you're outside of the parentheses there. Second graph, scroll back up to x equals 0. So the car initially is worth 20,000. After 1 year, the car's value drops to $19,000, then $18,050, $17,148, and then $16,290, and then it keeps going. So you can see as each year goes by, the car is losing its value. The question though is, in this equation, where does the 0.95 come from? So previously when we were dealing with percents and growth, we were taking 5 divided by 100 to get that decimal. And then we added 1 to it because that reflected the increase of the 5% being included apart with the initial value. This time you're going to take 1 and subtract 0.05. Because this time we're decaying, we're falling, we're depreciating. Any of those words mean the same thing. So we want to lose value. So we're not going to increase, we're actually going to lose. So that's going to become 0.95. So really, every year, the value of the car is 95% of what it used to be. And that's what we're calculating. So the only difference is, instead of adding 1, you're subtracting the decimal from 1. That's the big difference with these problems. And that's what leads to the graph to decay and look like that, as opposed to what we were used to before. So let's try another problem. Illinois has a declining population. If the current population of Illinois is 12 million people, there's my initial value. And it's decreasing at a rate of 3% per year. So remember, we do 3 divided by 100 to get that decimal. But since we're decreasing, we're going to subtract. So it's going to be 1 minus 0.03, which is 0.97. So the next year's population is going to be 97% of what it was before. That's your B, your multiplier, your B value. So to figure out the population in 20 years, we write our equation, and then we're going to plug in 20 for the x. I got 12 million times 0.97 to the 20th. So that gives me 6,525,532. I'd leave off the decimal because we're dealing with people in this case. So again, when you're doing these problems, think about your answers in terms of the context of the problem. We're saying that Illinois' population is decreasing. So it's decreasing 3% each year for 20 years. For your answer to make sense, this number should be smaller than the original number. And in this case, it is. You started with 12 million, and then in 20 years, it drops to 6.5 million, about 6.5 million. That's a decrease. So that's how you can check your answers. If you're decreasing, remember the big difference is with decay, you subtract from 1. Whereas before, we were adding 1 when we were increasing. So that's what we're going to work on for today is exponential decay.